Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's my pleasure to introduce Professor Guangbing Huang from Nanyang Technology University of Singapore, NTU. So he is talking about his long interest research in extreme learning machine. He graduated from Northeastern University in China in applied mathematics and has been with NTU for quite a few years. And he's the associate editor of Neural Computing and also attribute transactions on system man and cybernetics. And he's organizing a workshop. You can advertise your conference later on. So please go ahead.
Yeah. Thank Dr. Zhang for inviting me here. It's my honor to give a talk to introduce the extreme learning machine. This is actually, the idea was initially initiated in 2003. That was the first time we submitted papers. And then it became recognized by more and more researchers recently. So we just had a workshop in Australia last December. So we are going to have an international symposium on extreme learning machine this coming December in China, actually Dr. Zhang's hometown, or nearby his hometown. So welcome, you can join. Okay, so what is an extreme learning machine? Actually, this is a technique talking about the kind of learning method. Such a learning method is different from the traditional learning method. So tuning is not required, right? So if we wish to know extreme learning machine, I think it's better to go back to review the traditional feed-forward neural networks, including supported vector machines. Although many people consider supported vector machines do not belong to neural networks. But actually, in my opinion, later on I will show they have the same target, same architecture in some aspects, in some sense. So after we review feed-forward neural networks, then we can go to the to introduce what is called extreme learning machine. Actually, extreme learning machine is very, very simple. Okay, during my talk, I also wish to give the comparison between the ERM and the least square SVM. So finally, I wish to show the linkage between the ERM and also the traditional SVM, so that we know what's the difference, what's the relationship, okay? So the feed-forward neural network have the several types of famous architectures. One of the popular ones is multi-layer feed-forward neural networks. But then, in theory and also in applications, people found a single hidden layer is enough for us to handle all the applications in theory. So that means given any applications, we can design a single hidden layer feed-forward network. This single hidden layer feed-forward network can be used for us to approximate any continuous target function. Can be used for us to classify any disjoint regions. Okay, so for single hidden layer feed-forward networks, usually we also have the two types of popular architectures. The first one is the so-called sigmoid type of feed-forward network. So that means the hidden layer here use sigmoid of type network. Okay, sometimes I call additive hidden nodes. That means the input of each hidden node is a weighted sum of the input. Okay, so of course GE here usually people are using sigmoid type of function, but we can also write the output hidden layer hidden node as uppercase G, right? So AI, BI, and X. X is the input of the network. AI, BI are the hidden layer parameters for each. Say for hidden node I, the AI, BI are the parameters of the node I, right? So this is the sigmoid type of hidden feed-forward network. Of course, another one is very, very popular is RBF network. So RBF network here, the hidden node output function is RBF function. So, but if we write then in this computer format, we actually have the same so-called output function of the single hidden layer feed-forward network as sigmoid type network. So here also uppercase G. Okay, so these two type of networks is very interesting. In the past 2 to 3 decades, two group of people, researchers work on these two areas. They consider them separate. So they use a different learning method for these two networks. But generally, for both type of networks, we have this so-called theorem. So given any target continuous function, fx, so the output function of this single hidden layer can be can be as close as to this target continuous function, given any error. Definitely in theory, we can find such a network so that the output of this network can be as close as to this target function fx. Of course, in real applications, we do not know the target function fx, right? So in signal processing, we have a sampling. We only can sample the discrete samples. And we wish to learn these discrete samples, training samples. So we wish to adjust the parameters of the hidden layer and also the width between the hidden layer to the output layer. Try to find some algorithm to learn these parameters to make sure the output of the network to approximate a target function. Okay? So generally, from learning point of view, so given say n training samples, xi, so we wish to have the network output of the network with respect to the input xj equal to your target output tj, right? Of course, in most cases, your output not exactly the same as your target. So there are some error there. Suppose the output of the network is oj, so we wish to minimize this cost function, right? So in order to do this, many people, right, actually spend time finding different methods, right, on how to tune the hidden layer parameters AI, BI, and also the width between the hidden layer to the output layer, that is beta I, which is I call output width, right? So, so that is the situation for the learning. So that is for approximation, but how about the classification? So in my theory, published in the year 2000, we say as long as this kind of single hidden layer feed-forward network can approximate any target function, this network in theory can be used for us to classify any disjoint regions, right? So this is a classification case. Yeah.
So there's a very well-known result in neural network research, you probably know about, which says that in order for what you said, the universal approximation to be valid, the number of units had to be very, very large. And then if you get infinite you actually approximate what's called the Gaussian process.
Yeah, you're right.
So that gives a lot of implication of all the things you talk about here, right?
Okay, that is actually a very useful theory. That one actually is used for further development. So that is why we come to extreme learning machine. That is a guide, but the infinity number of hidden nodes usually not required in real application. But in theory, in order to approximate any target function, say epsilon, the arrow reaching 0, then in that sense, infinite number of new, hidden nodes needs to be given. But in real application, we do not need that. So I will mention later. But that theory is very, very important. Okay, without
Also, recently, many people observed that if you have many layers, actually you can make it better than a single layer system, even if you have very large number of hidden units in your single layer system.
You're right. So this, we have another paper, actually I didn't mention here, that is we prove, say, instead of say 3 hidden layers, just talk about 2 hidden layers, compare 1 hidden layer of architecture. So 2 hidden layers of network usually need much fewer number of hidden nodes than single hidden layer. So in I proved in theoretical and also showing in simulations. So that means that from learning capability point of view, multi-hidden layer looks more powerful, right? So, but that is, we actually is not shown here, okay? That one we can discuss later. Okay, so then in order to learn this kind of networks, so then in the past 2 decades, so most people using gradient-based learning method, right? So one of the most popular one is backpropagation, of course. And it's variants, so many variants. People talk about just some parameters, they generate another learning method, okay? Another method is called for RBF network. So talk about least square method. But in this least square method is some kind of something different from our ERM, which we will introduce later. So single impact factor used in all hidden nodes. That means in all hidden nodes, all hidden nodes use the same impact factor, impact width. Okay, sometimes we call sigma, right? Okay, so what's the drawbacks of those gradient-based method or so usually we will fear very difficulty in research. So different group of researchers work on different network. Actually, intuitively speaking, they have the similar architectures, but usually RBF network researchers work on RBF. So feed-forward network people work on feed-forward network. So they consider the networks are different. So we actually sometimes waste the resources. And also, in all the network, users, it's actually inconvenient to users because sometimes so many parameters for user to tune manually, right? It's case by case, okay? So it's sometimes inconvenient for non-expert users, okay? So it's usually we also face overfitting issues. So this is why if too many use the number of hidden nodes used in hidden layer, we will face a problem, overfitting problem, right? So we will face a headache, okay? And also, right, for RBF, a local minimum, right? So you can't get the optimum solution. Usually get a local minimum solution. That is better for that local area, but not for the general, the entire applications. Of course, time consuming. Time consuming not only on learning itself, and also on human effort. Human has to spend time to find the so-called proper parameters, user-specified parameters. So we wish to overcome all these limitations, constraints in the original learning methods. Now let's look at the spotted virtual machine. Is there any relationship between the spotted virtual machine and the traditional feed-forward network? Of course, when SVM people talk about SVM, they never talk about neural network. They say they're separate. So this is why there was a story. So when I joined IJCN in 2004, before 2004, SVM paper is seldom appear in neural network conference. So then in 2004, the organizer of 2004, right, the talk, we have a committee meeting, and say, why this year so many SVM papers come to neural network conference? Okay, so people consider these are different. But what I found, actually, they are very close to each other. In generally speaking, they are the same, in the same network architecture. Let's look at the SVM. So next SVM, of course, if we talk about the optimization objective, SVM is to minimize this formula, right? So this objective function, so minimize the weight, actually output width plus the training error under these inequality conditions, right? But look at the final decision of SVM is this decision. But watch this. K here is a kernel of the SVM, all right? Alpha STS is the parameter we want to find. Okay, but look at this formula. This actually exactly is a single hidden layer feed-forward network. What is single hidden layer? Single hidden layer formed by the hiddens with these kernels, right? So KX, X1, KX, X2, XI2, KX, XN. So this is the hidden layer, right? This is the kernel, hidden layer with this kernel. So what is the output width then? Output width is alpha 1 T1, alpha I Ti, alpha N Tn. That is the output width. That is the beta I in feed-forward network. Okay, yeah, please.
This was known from the beginning of SVMs. If you look in Batman's books, he has exactly this interpretation of SVM.
Okay, yeah, this is not objective of the SVM, but finally it turned out to be in this formula. So I say from the architecture point of view, so finally they had a similar architecture.
When Batman started working on SVMs under ARPA, the project was called New Ways to Train Neural Networks. So there was a connection from the beginning, and it was exactly this.
Yeah. So actually, yeah, you will talk about the Wapnick paper published in 1995. So Wapnick, what is the so-called inspiration to Wapnick? So Wapnick say actually these have to go back to the original neural network. Okay, so Reznor actually in 1962, Reznor studied a multi-layer feed-forward network. In those days, he found has no idea how to tuning the hidden layer. So then Reznor said, how about we consider the last layer, ignore the hidden layer. If we consider last hidden layer is output mapping function, looks output mapping function. So then can we find some way to just find the output, the last hidden layer output function, that is feature map function. Then ignore the rest. So then Wapnick say, okay, so what is so the output function of the last hidden layer, or that it can be considered is phi xi. But what is phi xi? I have no idea. So then in Wapnick paper say, how about let phi x unknown? So we have this kind of constraint because this is very important for classification. Under this constraint, they finally get this. So although the output hidden layer mapping function, that is the SVM feature mapping function phi x is unknown, but we can find the corresponding kernel. So this is why I come to this stage. But actually, I'm not challenging the idea of SVM. I'm talking about from a structure point of view. If we go to this stage, finally turn out to be in the same format. Of course, from here, the question is how to find alpha ITS. How to find alpha ITS is how to find this output width, right? So you will consider the hidden layer feed-forward network. Feed-forward hidden network also try to find a parameter. So SVM and the traditional BP and so on, in this sense, are just different ways to find the parameters of the hidden layer feed-forward network, single hidden layer feed-forward networks. SVM find it in SVM format, BP find it in BP format, RBF find it in RBF format. So this is why different people find methods in different ways. So then the question is, can we unify them? Okay, so this is one of my so-called research work. Okay, actually, in order to say to show the linkage between the SVM and the single hidden layer feed-forward network, I think people better read these two papers. Okay, because these two papers also give me some idea, inspire my ideas. They build the linkage between the ERM and SVM first. So then I found this linkage also. Okay, so now let's go to the talk about extreme learning machine. Of course, extreme learning machine originally started from the neural networks. We come from neural networks. So those days we try to say, okay, we started from BP network. So BP we found is inefficient. But what is the essence? What is the original expectation for neural network? We try to emulate human thinking. But human can think something, can find a solution very quickly. So the question is, do we have tuning in human brain? But usually, to me, it's no tuning there in most cases, right? Just find a solution directly. Or I can learn very fast, right? Either very fast, either without tuning. But you need to go back to the original learning method of the neural network. Supervised machine, you see, always tuning there, right? Always have to find a parameters there. Can we have some way to simplify the implementation of the computational intelligence method? So then we found, from all these architecture point of view, we see all can be simplified in this single hidden layer feed-forward networks. So all with hidden layer, right? AI, BI, but hidden layer here, hidden node may not be neuron. It can be a kernel. It can be other sub-network even. But each hidden layer has a parameter, AI, BI. Those are the parameters. If we ignore the real formula of each output output function of the hidden node, right? Details, we just write them in this compact format. Okay, so then the output of this output function of this network is fx equal to summation of beta I GAI BIX. GAI BIX actually is the output function of the I's hidden node. Okay, it can be RBF network kernel. It can be so-called the sigmoid type network, if something else. Even can be non-differentiable network, threshold network. Okay, so then you see this hidden layer, the entire hidden layer. What is the output of the entire hidden layer? The entire hidden layer. Suppose the entire hidden layer has AO hidden nodes. So then the output layer. What is the output layer? The output layer is HX. Is the vector of these AO elements of this the output functions. Output of these AO hidden nodes, right? It's a vector. HX here is the feature mapping, is a hidden layer feed, so-called output mapping, right? Okay, so in this case, the question is, in the traditional method, AI, BI, AL, A1, B1, AL, BL, all have to be tuned. So this is why we have to have the gradient-based method or SVM method, because you see, if this parameter hidden layer has been tuned, the result you obtain in the early stage in the output layer, right, beta I here may not be optimum. You have to adjust the output layer again. If you adjust the output layer, the beta I, beta 1 to beta L, then the parameter in the hidden layer may not be optimal further anymore. So you have to adjust it again. So this is why you always have to adjust, right, iteratively. So then luckily, in our theory, we found tuning in the hidden layer actually is not required. All the parameters in the hidden layer can be randomly generated. This go back to your. So this assume infinity number of hidden nodes can be used. Of course, this is assumption, but actually we do not need. Okay, right? So this also go back to the SVM. SVM is go to the feature space. Suppose the dimension of the feature space is very large. What is very large? It can be go to infinity, right? So that is why they have the kernel concept there. So if we say if the hidden layer can, so number of hidden nodes in the hidden layer can be infinity, okay, or as large as possible, then the question is, then we have this conclusion. So tuning is not required. All the parameters in the hidden layer can be randomly generated. This is based on another assumption. Say suppose given an output function G of the hidden layer, if there exists a method, okay, which can be used to tuning to find the proper parameters for AI BI. So that means there is a parameter. We can have a parameter. We have a tuning method, BP method, RBF method, or SVM method, whatever method. As long as there exists such a tuning method, which can be used to training or single hidden layer feed forward, okay, then such a tuning is not required. Such a method is not required. Hidden layer can then be randomly generated. That is given in this paper, okay? So, and also another assumption is G here should be nonlinear piecewise continuous. You can't just give a delta function, then no way. Yeah, please?
Can you explain the difference between AI and BI?
Okay, so this I highlight AI, BI. Sometimes they can be put together, just one parameter, okay? But AI, BI here, because usually in a traditional neural network, you see RBF network, you have center and impact factor. So AI here in the RBF hidden node, AI is center, BI is the impact factor. If we go to sigmoid function, AI is the input width, BI is the bias of the hidden node. So this is why, because these come from the traditional neural network. So especially for neural network researchers, usually they have two parameters there. So this is why I put AI, BI. But if you go to the frequency analysis, usually you have the position and the frequency, right? Not the location and the frequency, right? So usually have the two.
What is it for SVMs?
Oh, for SVMs, SVM, if you talk about kernel, later on I was showing kernel, you have the so-called AI is the input that is called sample, training samples. BI is so-called we call kernel parameter, that is sigma. But of course here we are talking about random. So later on we can build the linkage between SVM and this method, okay? But of course here we are talking about random first. Okay, so yeah.
Excuse me. For any application, do you need to tune error, or you don't need to tune it?
These I will address this issue later. Yeah, these are important questions. I will come back. Yeah. Okay. So since all the hidden node parameter need not be tuning, actually not be tuning in the sense, before you see the training data, you can randomly generate the parameter first. Okay, then say for this application, you can use the already random generated hidden nodes for that kind of application. That means the parameter can be independently from the training from your applications. So since AI, BI, all the parameter, hidden node parameters can be randomly generated, then go here. Say suppose you have n training samples. Given any training sample xj, so we wish the output of this network equal to your target, Tj, right? The left hand is the output of the network. We wish this equal to your target. So we have the AO hidden nodes. So here we have AO unknown parameters then. Only AO unknown parameters, beta I, because we have no idea what is beta I. That is we want to find. Although the hidden layer can be randomly generated. The Tj is your target. So we have the n training samples. So from here we know we have the n equations with AO unknown parameters, right? So then for these AO equations, we can written it can be written in the compact format, H beta equal to T. So H is we call hidden node output matrix, right? It's also the so-called the hidden layer mapping, okay, feature mapping, okay. So we have the n training data, right? So each row represents the output of the hidden layer with respect to one input training xi. Okay, so we wish to t is already given. We want to find this parameter. So for this, h beta equal to t. H is already known, t is already known. So then we can find the parameter beta easily. 3 steps then. So the first step, randomly assign hidden node parameters ai, bi, and then calculate the hidden layer output function matrix h. All right. So then just do a pseudo inverse, get the beta. That's all. So these are 3 steps. Okay. So the source code can be found here. For this, we have found the simple math is enough in many cases. Of course, then for this single hidden layer feed-forward network, the hidden node, okay, needn't be sigmoid type, needn't be RBF type. It can be others, non-threshold hidden node, because previously the threshold network can't be trained, okay, directly. So with this method, threshold network can also be trained. But that is a basic idea. So now, what's the relationship? Yeah.
In the statistics community, there's something called generalized linear models, where you take the input data, you map it to some nonlinear thing, and then you take a linear combination, which looks exactly like this. So how is it related? How is
excuse me, what is a nonlinear?
Generalized linear where you basically map the data to a nonlinear form, and then take a linear combination of the works and find a linear combination. So it looks very similar to this. So I'm wondering what the difference is.
Yeah, so this why, so many methods actually look similar, but the key point is here, the hidden nodes here, all randomly generated. Because in other methods, they have to so-called either user preset some parameters, or either tune in some way, then get the hidden layer output. So then they use the least square method, even the original RBF method. So they have to do something before they go to the random generated from, yeah?
When you say that taking random hidden layer is enough, then I don't understand what is enough means. I mean, does it mean that you get uniformly good approximation across the input space? I mean, this can't be a distribution-dependent thing. You can't get actual learning from this. This has to be assuming some type of uniform distribution on your input space.
Okay. Well, is enough to talk about here. Say, given any target function, continuous target function fx, we can say, for given such a kind of single hidden layer feed-forward network, may not be neural network, okay? So as long as the number of hidden nodes is large enough, we can say the output of this single hidden network can be as close as to your target function. So given any target function, any continuous target function, so that we can make the output of the network as close as to your target. So this is, because from the learning point of view, in theory, we wish to have this universal approximation property, right? But give a network.
I think what you want is to get, to learn the specific distribution of the problem you have at hand. So this is some kind of extreme L infinity type of, you're talking here about a uniform convergence right across the entire space. Whereas you may actually care about some little part of the space which is governed by the distribution of your samples. I mean, that's what's supposed to, that's what's the difference between optimization and learning, or approximation and learning.
You're right. So talk about, say, given entire, so here talk about the score error in the entire interested space. Of course, talk about so-called some specific space that could be different. So this problem true to many learning methods, even go to the BP. They also talk about general. Even SVM talk about the overall space. Given this region, we wish to learn to see how good in this entire region instead of specific so-called locations, area, small area. But that is a problem to the general learning method. Because learning method usually say, give a space, given this training data, untraining data, we wish to learn the overall performance on this untraining data. Of course, sometimes we are also interested in some particular subsets, but that is different ways then.
I don't think you understood what I said. When we get a training set, we care about the distribution from which that data set came. We don't care about uniformity across the space. And an SVM specifically has an analysis. So the only learning and generalization analysis for SVM talks about generalizing with respect to the distribution of the training data, not uniformly across the space.
Okay. You're talking about distribution of the training data. In which sense?
In which sense? You're assuming that your sample is IID from some distribution. That's a distribution with respect to which you measure risk and you want to generalize with respect to. You don't really care about doing anything uniformly across the entire space. In SVM, for instance, the space is some infinite dimensional thing, and all you really care about is the subspace spanned by your data and the distribution over that subspace. So
okay.
Here, this is kind of a, you know.
Yeah, okay. I will go back to your question later, because later on we have a comparison. So why they find it can be so-called, even so this square SVM can be simplified to this stage. Okay, I come back later. Yeah. So that is the 3 steps. But then we talk about these 3 steps. So usually after we get a beta can be, say, calculated through the pseudo inverse format. You have a different way to calculate pseudo inverse. So one of the ways is get the orthogonal method. So we say we have the pseudo inverse of beta can so-called the h can be in this way or in this way, right? But from the rigid regression theory point of view, in order to improve the stability, improve the performance of the pseudo inverse, so usually we wish to add a so-called some constant value in the diagonal entry of this part. So then we can add here, right? So after we add this one here, because this one is the usual way for us to handle the pseudo inverse. So what's the relationship with SVM then? Okay. So after we add this, then the issues become very interesting. If Hx is long to us, this is different from SVM. In SVM, Hx usually is unknown. So if Hx is long to us, then we have this. All right. If Hx is unknown, we can also use the same format. We can use a kernel format. So from the first formula, so h times h, then we get this kernel format. In this case, as long as k is known to us, even the feature mapping function hx is unknown to us, we can get this formula. Okay, so this is another formula from ERM, from the ERM. Okay, we mentioned in this paper. So then what happens then? You compare these two. This is the solution of the ERM. This is the solution of the least square SVM. This square SVM, you see, if we ignore the first row, first column of this square SVM solution, this part actually very similar to this part, right? To ERM solution. But then here, of course, here we have the k times k, here is z times z. So they have this one, okay? So roughly looks similar. But this actually is a simplified version of the least square SVM. Why this is a simplified version? This actually mentioned in this paper. Because we found they may have some flaw in least square SVM and the SVM series I will mention later. But you look at the least square SVM, so you have the T, so Z here actually is a kernel matrix. Omega here is a kernel matrix. But then the problem is why in their kernel is a matrix is related to the feature mapping. It should not be related to the target. But in their feature mapping, kernel mapping actually is related to the target. But this is the problem. So your feature mapping is coming from the input instead of you have feedback from the output, right? But in their solution, they have TI. So T, you have a target in the kernel mapping matrix. Okay, so this is a problem there. But then from here, we have simplified. We ignore the first column, first row, first column, then make it simple, right? So I will come back later. So why this one actually can be so-called can be discussed. It may have something which can be improved somewhere. Okay. So now let's look at the classification, so-called the performance of the ERM. So now let's look at the XOR problem. All right, so this is the output boundary of the ERM, which found by ERM. So we look at another case, right? This is also a boundary found by the so-called ERM method. So now go back to your questions. Do we need an infinite number of hidden nodes? Usually not. So we say, so as long as the number of hidden nodes is not enough, then okay. So in what sense not enough? So in all our simulations, say even for this case, we only have 4 training data, 1,000 hidden nodes. Even here, you have, say, here maybe 8,000 data, 1,000 training data, 1,000 hidden nodes. Even for other cases, sometimes we have half a million of training data, okay, case. We also just need 1,000 hidden nodes. So in that means, usually 1,000 enough. 1,000 to 2,000 should be fine for ERM. Usually, this what we find. Yes.
Is that an empirical observation, or do you have a theory that actually suggests that that's?
Oh no, we do not have theory. This is just from our experimental simulation. Also, not only found by us, also found by some other teams from Europe and China. Yeah. So.
Does that depend on dimensionality? The number of nodes, you mentioned 1,000 is quite good. So is that independent of the dimensionality?
Okay. For the moment, we found it looks likely independent from the dimensions. Because sometimes later I also show you some is higher dimension, some is lower dimension, some is even several thousand. Also okay. Oh yeah.
And also, when you say 1,000, do you mean you need 1,000 to match the performance of a regular SVM?
We also compare with SVM, regular SVM later.
But what performance? What I'm asking is, what performance are you trying to get? I mean, I could have 2.
No, we have this. We wish to compare with the traditional SVM in the same meaning. Say if they have the dimension related reduction, then we compare in the same way. If they do not have the dimension reduction, we also compare the performance without dimension reduction. We wish to see if talk about classification, we want to see the classification rate in the testing data. Yeah.
Match error rates.
Yeah.
With the standard methods, and for that, 1,000 hidden nodes is enough usually. You say.
Sorry.
If I understand you correctly, you're comparing against standard methods. You want to match the error rate. You want to get the same error rate. And to get the same error rate, you need 1,000 hidden nodes with ELM.
Yeah.
So what's the largest? Sorry, I'll stop to it. What's the largest problem you apply this to?
Okay, so this is a problem because you see, ERM, the scalability actually is very, very good because you see the function, that calculation is very, very simple. You look at here. This actually is unified for multi-class, multi-label classification also. But this here, similar to SVM, is just for binary. So if we want to handle very large case for SVM and this square SVM, usually we have so-called 1 against all, 1 against 1 kind of method for both SVM and this square SVM. So usually we have to find the supercomputer for very large case. But to us, we usually run it in the home computer or just the desktop in the lab. So for our on-case, the largest one we run is 500,000 of data. With each so-called data instance is say 59 input attributes. I will mention later. But for the rest, because due to the so-called computing environment, sometimes very difficult. We have to sometimes wait for months to get the result out. So this is a problem. But for us, just several minutes, we get a result. So sometimes we can't put the result there because we have to wait the rest.
So all the compute you reach probably apply up to 500,000.
Yeah, the maximum. I will mention. I have one slide to show it. Okay.
So what do you have in terms of the variability when you try different set of random parameters?
For the moment, we have
like for the first one, if you try different parameters,
you
usually have different kernel parameters. A, B, I.
Yeah, that's right. We usually have to run. We in order to compare SVM and other methods, not only SVM and BP. We actually, just the hidden number of hidden nodes. That one usually can be just given, then run for all. But for the rest method, you have to tune in this method, tune in that method. In order to find one method, even given one method, they have to spend a lot, so it will cost a lot of time for them to complete.
Procedure-wise, I actually have the same question as Jenny. When you actually use a random generator to get this AB, how many runs do you have to get?
Okay, use just one.
But you get a different result.
For the result here, later I show, we can generate many times. We see the average. We can see the average.
I see. So do they differ a lot?
I will show you that. There are some standard deviation. That is a very interesting result. You will see it. Okay, let's look at these several data cases. Actually, not very large. Okay, so they say they have this case. Say the training number of training data for letter recognition is 13,000. Then testing is 6,000. Okay, so then this number of the input features, then class is here. So yes means the data can be so training data and testing every time during a trial are reshuffled. The rest no means no shuffled according to the simulation done by others. If training data fixed, testing data fixed. Okay. Now let's look at this case. So if we talk about the let's look at the lower part first. If SVM, this square SVM and ERM all use Gaussian kernel. Gaussian kernel here is not random generated. You look at the earlier solution here. I say if the HX is already known to you, you can use these two formulas. If HX is unknown, similar to SVM, but to us is needing to be tuning, right? So we can use the same format here using the kernel format, right? This is different from this square SVM. We can also use a kernel here because usually here no tuning, just usually one parameter. Of course, for any method, no free none, you definitely have to do something for some, right? At least one parameter. So if we talk about a kernel, Gaussian kernel method, you see, look here. This is the testing rate for SVM. Okay, so this is a training time. This square method, you see the ERM. For all the method, for all the data, the ERM achieves the better generalization, the testing accuracy, classification rate. Okay, you see here, all better here. You see the time, if the same Gaussian kernel, this time actually is all shorter than the SVM and this SVM. Of course, this square SVM is much shorter than SVM. Okay, so this is the using a kernel format, right? But if you see the standard duration here also 0, because the training data is fixed, right? Testing data is fixed, right? So then these three methods have the same, almost the same standard duration.
Like you're choosing the widths randomly?
No, this not count. This count. This we want to intentionally compare SVM, this square SVM, and ERM. If they use the same kernel, that means compare them in the same scope environment. Of course, you have to choose the parameter gamma impact factor for all these three methods, right? So this is the one comparison. But if because ERM here, we say the hidden layer output function is unknown to us, but we can use in the kernel format, similar to the SVM, just kernel learning. But if the HX is known to us, it seems the RBF network, sigmoid network, the traditional neural network. So then we say we just using one method, sigmoid hidden node, right? So then all the parameters are randomly generated. And the number of hidden nodes is set as 1,000. Then what happened? You look here, it's very interesting. You see the classification rate here also higher, almost better than all the rest, right? And then, of course, because they're random generated, so some standard deviation here, right? Even the training data is fixed, testing data is fixed. You still have some kind of variation there because it's true. Because every time you random generate, they have some kind of variation there. But you see the deviation is not so high. All right? Yeah. Please.
What vectors did the standard methods get?
Support vectors for this. Actually, this one, I think it can be found from papers. I can't really remember. But usually,
well, the only reason I'm asking is if at runtime, it's going to be slower if you have 1,000 versus 10.
You're right. Next page I will address your comments, your concern. Okay, I will go back later. So you see the training time. So the training time here is much shorter than the SVM, and this is square SVM, even shorter than the ERM with Gaussian corner. Because when you go to Gaussian corner, you see usually we consider the feature space go to infinity. I mean, in theory,
so
but here
it's comparing the sigma hidden node versus kernel. Do you have general statement as to which one is better in terms of performance versus
okay? In terms of classification, in terms of stability, Gaussian corner is better because all you see a standard deviation here is 0. Whenever fixed, training data fixed, then the result is definitely deterministic. All right? But in terms of time, training time, this is better. Sigmoid, hidden node. That means so-called long kernel based is better because the kernel usually we need to give we need to give too many hidden nodes. So usually 1,000 enough. But 1,000 enough, very good for very large applications. Because when you go to a very large application, the scalability of SVM and this square SVM will be very headache, troublesome to us. But then ERM is better, right? So this is.
So I'm thinking about what you are doing now there is to use the random this sequence and all this whatever either sigma to extract features, right? Mm-hmm. And after that you just linear classify at the top level.
Yeah.
So why is that feature a good one?
I will explain to you.
Intuitive.
Yeah, it's not. Even in the beginning, when I thought of this idea, if I question myself, can it work? I can't find any natural phenomena at that stage. But now I found the natural phenomena. So I say this is a natural learning skill. I will go back later. It's very interesting. I will go back later.
So, by the way, so when you use SVM, the number of support vectors will be automatically determined, right?
Yes.
This number will be considered as the number of hidden units in your ERM. So do you have idea what is the number of support vectors you get with the SVM?
Okay. Usually for SVM, what I found is in some order related to the number of training data. If we talk about regression method, usually half of the training data will be used as the support vectors. Go to this page. I just run a artificial case SciC function, right? Usually as a very important benchmark problem to test the SVM performance, right? We have 5,000 training data and 5,000 testing data. So training data, we intentionally add some noise there. Test data is noise free. So if we go to SVM, of course here we change it to support vector regression because for regression case. So you have the 5,000 data, training data, you see here, nearly half of them used as the support vectors. All right? So this is why even in other case, we all usually say the number of support vectors is very comparable to the number of training data. So we talk about very large scale, large data set. The number of support vector will be very huge. So then these go to the runtime issue raised by this gentleman, right? So you go to testing. The test time will be very huge for support vectors, and this is square SVM. But while the number of hidden nodes in SERM can be very short. Look at this case. Instead of fix them as 1,000, I just choose 20. You see the testing accuracy for this case, ERM already short smaller than, is better than SVR, right? The training time here is 10, actually is 0.1 seconds. You see the SVR is nearly 20 minutes, all right? So this is, yeah, please.
If you use, say, 1,000 on ELM in this case, would it maintain the same accuracy or would it overtrain?
Okay, these are different methods then. Because we all have the different versions. ERM always under developing. Here, for this case, we use, because it's probably in the year 2006, quite a long time ago. For that case, we did not include the constant value in the diagonal entry of this of H, right? We do not include this I over C here. We're just using using a formula without I over C, this part. For that, without that diagonal entry, you can given the number of hidden nodes. So then the number of hidden nodes, if you go back to see this paper, different from the backpropagation method. Backpropagation method is very sensitive to the number of hidden nodes. All right, you can go to the peak performance easily, quickly, then drop down quickly because overfitting there. But what is ERM usually have a very large range. So the performance, the general performance is very stable in a very large range, and then slightly deteriorate. Okay, of course, the number of hidden nodes in that sense, number of hidden nodes required in ERM is higher than number of hidden nodes in BP because every hidden node in the BP have to be tuned carefully, but to us random generate. But why is this so stable in a very wide range for ERM? Because everyone is random generated. So you add one more or one less, usually more or less there. So in that sense, intuitive scaling is more stable. This is why we have a neural network. Original, the intention of the ERM, we should be so-called tolerance. We should have some kind of redundancy. We should have some kind of error tolerance, right? But for the original BP, it does not have this feature. Yeah, yes, please.
So in that sense, there's no real tuning parameters?
Yeah. So we usually, in this case, we're just using a golden section. Say 10 hidden nodes, too little, too few. Count, because incapable of learning. 1,000 too few. They just said 500. Just 3 steps usually in our simulations. We do not have to be carefully tuning everything. Yeah. So this is why even say in this case, number of hidden nodes have to be given, but usually can be given very easily, just using a golden section. Okay. Of course, this is for regression case. I want to repeat anymore. Compare with BP, compare with ERM and spot vector machine. Okay. Now you look here for parameters. BP, you have to tune in the parameters here. Of course, you also sometimes have to tune in the number of learning approach. Then the SVR, you have to tune in the parameters. ERM, for that traditional one, you have to give the number of hidden nodes. Of course, after we add the diagonal entry in the formula, number of hidden nodes can be fixed. Say just 1,000 without doing any tuning here. Okay?
Then you need to tune C, right?
You are right. But C, yeah, definitely. That means either you're tuning, tuning number of hidden nodes here, but of course this is not sensitive, or either tuning C. But C also not so sensitive compared with SVM. That means you have to tuning, but it's not so sensitive compared to SVM. Okay, these have to. Yeah.
Go back to that. So this slide seems like to suggest you need to use much more number of hidden units than the BP.
You're right. I just mentioned because the number, so-called number of the hidden, the rules of each hidden node in the BP have to be already calculated carefully by the BP, or it's just random. So sometimes it's random, redundancy is there, but redundancy is good, help us to remain stable in some case, right?
So my question is, for large problems or huge problems, will this cause any problem?
No. There you see even here, not too many even. If you compare with SVR, not too many. But as I just mentioned, if after you add the diagonal entry, number of hidden nodes can be fixed. Usually we just fix 1,000, right? In almost all the test cases we have so far, just remain them.
Yeah, so let me just have one question. I think this is bothering me all the time. So suppose you compare the same network topology, the same number of parameters, all that. And the way you are doing that, you fix the earlier parameters by random number. Yeah. Then you optimize the one the top layer. Right? Yeah. And then, of course, you are not going to get as low error as I do both. Right? Optimize both. Right? I could actually fix whatever you have at the top level better. And then I can still have freedom to train the other one. I will get better result in the training one. So are you talking about the training result, or are you doing the generalization issue?
Great idea. So, question. This depends. So it depends which algorithm you are using to train your network. Say if you're using BP, then you're stuck in the local minimum. Even you can't go to the global optimum.
Oh, I'm saying that have you tried this experiment? I think I would, certainly would do that. You use whatever method to get whatever good result, okay? And then you fix better that you get.
Yeah.
And then I fix those. I do backpropagation BP to train my AB so that it won't be the same as what you randomly generated, I actually get better.
BP won't get a better result in most cases. It may get a better result in some cases. What I say, it won't get BP won't get a better result in most cases in terms of accuracy. Okay.
No, I'm saying that. I mean, given that I use the same parameter that you learn at N, I still have more freedom to adjust other parameters. I may not have to do BP. I will just use any even greedy search. I might get some lower error. Is that going to give you?
No,
so,
definitely.
The issue will be generalization rather than the trend.
Definitely, BP will get a lower general performance. You see why? Because when the BP have to tune in all the hidden nodes, in ERM, hidden nodes is randomly generated, okay, in most cases. BP have to tune in all the parameters. Say we have 1,000 hidden nodes randomly generated. For ERM, it works. Then go to BP, overfitting. Because, say you just have 100 data. You have using 1,000 hidden nodes. Then this network definitely can't learn this 100 data because number of hidden nodes is larger than number of training data. It's impossible, right? The training data, training error can go to 0. Then testing accuracy can be even go to infinity in some sense. Very huge because overfitting there. But the ERM is random generated. So in which sense why the ERM is better than BP? Of course, later I can give you other reasons. One reason is here. When we generate the hidden nodes, we do not give the preference to training data. So that means the hidden node can be generated without seeing the training data. So let's see the testing data and the training data in the same rule. Give the same priority to the same. But in the BP, hidden node is tuning the baseline training data. In other words, you give the priority, give the advantage to the training data, give the bias to the testing data. So in this sense, BP actually is over focus on training data, right? So they do not balance the training data and the testing performance, testing data. So in this sense, the BP is not good, okay? So similar to other method, okay? Now, you look at another larger case. This also appeared probably in 5 or 6 years ago. So we have this, say, Harvard actually is nearly 600,000 data. So 100,000 for training. Actually, later on we also tested for Harvard meaning. You see here, SVM spent 12 hours for one trial. That means suppose we already found the best parameters or optimum user specified parameters. Then how many number of hidden nodes, number of super vectors? So here you have 100,000 training data. So here is 1/3 of them used as super vectors. All right, this go back to the gentleman, right? So that means for the runtime case, the testing time will be very huge. So even you have the training network, given application, the product or application based on SVM may respond very slowly compared to ERM. ERM only 200 enough hidden nodes for this case. Then for each training just 1.6 minutes, right? But look here, that here is roughly 12 hours for one trial. But in order to find the appropriate parameters, you have to run maybe 200 times to find the best parameters. So usually we have to spend 1 month to get SVM complete. But for ERM, as what I say, just several times. Okay, so this one. Now, let's go back to here. Why ERM is better? So for the key expectation of ERM is hidden layer need not be tuned. Okay, it can be generated before we see the training data. This is the first key point. Second key point is hidden layer HX should satisfy universal approximate condition. Even I just mentioned, even HX is unknown, we assume HX should satisfy this condition. And if HX hidden layer does not satisfy this function, that means given some application, you can't approach it, you can't solve that application. Then what should we use? Why do we need to use this method, right? Okay, so then we want to minimize these two. Actually, this is similar to SVM, but this comes from neural network theory. actually published quite a long time ago. Okay, this is proved by a so-called actually UC Berkeley professor. UC Berkeley professor say we should, if the training error is already smaller, we try to minimize the width of the norm of the width of the whole network. So then I combine then these two. Why not minimize training error as well as minimize width of the whole network, right? So this then why we come here. In order to address why ERM is better than SVM in most cases, we compare least square SVM. From that, we can't see the why, the reasons. Okay, we go back to the original SVM. Original SVM actually talk about this kind of optimization target with inequality conditions, right? If we go back ERM, we also use the inequality conditions. But we know HX satisfies the universal approximation condition. So we have in ERM, we have this target function. I mean, this is analyzed from optimization aspect. So then we also have this condition. Look here. This different from SVM. SVM here add a B there, right? But in ERM, no B there because by HX satisfy universal approximation. Given any target in the feature space, suppose the separating boundary should pass through the origin in the feature space. So without a B, then we have this dual optimization problem for ERM. We only have this condition. That means in order to get a solution for ERM, we only need to find the optimal parameter alpha I in this cube from 0 to C. But look at this analyzed in this paper. Look at the SVM, the problem comes. Because phi x in SVM is unknown. But unknown, that means they even using polynomial method. Unknown, that means you may not be, phi x count may not satisfy universal approximation condition. So this is why they have the B, because in the feature space, right, the separating so-called boundary may not pass through the origin in the feature space. So this is why they added the B there. After they added B, the problem here, in the dual optimization problem, this condition will be generated. But if we generate this condition, then SVM faces a problem. In order to find the optimum alpha I Lagrange parameter, how do we find? Not only in this cube, also have to find the parameter in this hyperplane. This hyperplane defined by this condition. This is why we have SMO method, right? To find the best parameter along this hyperplane in this cube. Look here. ERM find the optimal solution, alpha I, in this cube. SVM find the solution in the hyperplane within this cube. So which one has a better optimal searching scope? This should be better, right? Because this solution, optimal solution here, definitely not better than the solution here, all right? So then why this problem comes? This is why in my brain, of course, this I just added this morning, and not published yet, so I wish to bring this idea here for discussion. Is there any flaw in SVM theory? Look at the SVM. SVM is very great. I appreciate this work. Without SVM, definitely computational intelligence research may not be so attractive, right? Okay, but the problem is SVM always search the optimum solution in this hyperplane within this cube, right? As I mentioned before, right? So then the problems, given two irrelevant applications, they may have to search the optimal parameter in the same hyperplane. Say I give the two applications, x1, x2, x1, t1, x2, t2, okay? Application 1, application 2. One talk about weather forecasting. One talk about human face recognition. Totally different, irrelevant applications. But their target may be the same, whether good or not. this face recognition, this man, yes or no, right? So the target is always T1, 0 or 1, 0 or 1. But according to SVM condition, they have to search they have to follow so-called search the solution in the same plane. Even that these two applications different, but their TI, target, class label may be the same. Right? So that means summation alpha I TI equal to 0, this condition is the same because TI is the same. Okay, weather forecasting, 500 data. Face recognition, 500 data. So in the weather forecasting, half of TI is 1. Half of TI is 0. Face recognition, target, half of them 1. Half of them 0, possibly, right? So then TI is the same in these two applications, but the applications are totally irrelevant. Input XI quite different, dimension different, distribution different. But then the searching area of the TI, alpha I, same. So this looks not so reasonable. Different application, why the searching so-called area the same, searching scope is the same.
But if the goal is to separate two classes, why is it not a good idea?
This is a problem. Because they are different applications, input dimensions, distribution totally different. So here, they only talk about the alpha I. Alpha I should be some parameter for us tuning. This should not only be related to the target. Also, if you want to relate it to the training data, you should relate it to the target and also some way input.
Related to the training data because you optimize for another goal. This is just a constraint.
You're right. So this is only related to the target. In this sense, in other words, give the preference to the target. This is what I want to say. It's good to relate it to training data, but only related to the target at this stage. Either you relate.
I mean, it is related to the training data because here this is just a constraint. You have the optimization goal, which is related to training data.
You're right. But for you will go to the relation optimizing goal here. You see here, right? This is the optimize. So from here, this part only related to the target. But of course, I can't say this is totally wrong. What I found, my sense is, it gives the similar BP. It gives the preference to the target. It looks two different applications. They want to link. Even their input distribution dimension totally different. But due to their similarity in the target, so they match them, make them close to each other. This is why I have some kind of so-called reservation, some kind of hesitation on this part, right? This may not be totally wrong. This is why I put the question here. Is this reasonable enough? Okay, but then the reason is what I've analyzed, because this I for discussion only. Okay, I haven't published this. This I come from this morning. Okay, after I wake up. So because SVM is too generous to the feature mapping, 5x is unknown. So in all the literature of the SVM work, you can't see say 5x has to satisfy universal condition. They can be anything. You say polynomial, even x squared can be used, right? Sometimes, right? But you can see that one definitely. If you go to infinity, the output function, output of the later work can go to infinity also, right? So that may not be reasonable. But because the features mapping is unknown, so then they can't unknown. Since unknown, they have a bias in the output because your target is here. Your output, your feature mapping is unknown, so they have some bias between the distance between your original target and your actual target. Okay, actual output. So you have bias there. Because this bias there, so I think this is kind of contradiction. Of course, this has to be verified further. This is just for internal discussion. Okay, yeah, we can discuss later. Okay, so this is go back to this method, right? Go to even this analyze. We go to this method for ERM. It also works in this sense. We see here. We give some kind of classification testing case here. So then we see SVM method, ERM method. Of course, for this case, ERM, we set the number of hidden nodes as 1,000. Then C had to be tuning, right? Had to be given. Then SVM, Gaussian, you have C and gamma. Of course, for ERM, we also can use Gaussian kernel. But in order comparison, I didn't use the Gaussian kernel for ERM. So you see here, testing rate roughly is always better than SVM. So that means they are comparing the same method. Here, ERM not comparing this square SVM because both use inequality constraints. Of course, if we go back earlier slides, we are compare the same method in this square method, right? Or the metric space.
So the data size roughly is how much in those tasks?
Yeah.
Oh,
yeah, this just show. Yeah, just this is not showing the large data set. Even for here, for we say the high dimension gene selection case, right? So we have this result. Okay. Of course, that is for ERM. For batch learning means all the data are ready. But in real applications, even especially in so-called industrial applications, right? So many data are coming one by one or chunk by chunk. You do not know how many data you will have and when all the data will come. So this is a situation. So how do we implement something online? So this is why we have another one called online sequential ERM. Just to give one slide here to introduce a picture. So the data may come in one by one. Okay, they come in a chunk. The chunk size may be wide, maybe varying, maybe just one, maybe sometimes 20 data coming, maybe 1 million. Sometimes next time you just have so-called 500 data coming, right? So we wish to have a little one which can just learn the arriving data. Okay, as long as this arriving data has been learned, this data should be discarded, should be removed from your system, right? So next time when the data come in, you should learn the new data with the knowledge which learned from the past data, from the historical data. But after all the data learned, data should be discarded. It is very similar to our learning skill. Say we study from kindergarten to the PhD, okay? So every semester we have new textbook. When we learn the new textbook, we go to the examination. Hey, this is a chunk of data. After we pass the examination, we discard the old textbook. We learn a new textbook, means a new chunk of data, right? But when we learn a new chunk of data, we learn some new data with the knowledge learned from the old textbooks. But do we need to go back to the old textbook? Of course, you can review the old textbook. Usually, just learn one, then ignore it. So this is the very natural way. So in this sense, we can implement this online sequential learning based on the original batch learning mode ERM. Okay, I just skipped this part. Online sequential learning is very challenging to SVM and other methods. Usually, many parameters have to be tuning manually, so very difficult to handle. Okay, even the training time is very huge in many cases, very trivial, very troublesome. So with the ERM, this can be done very, very easily. Okay, so I just skipped this part. Okay, so then give a summary. Oh, sorry, time. So usually it can be done without tuning. Of course, we say without tuning means you have one insensitive parameter, say number of hidden nodes or the so-called the complexity penalty C. But usually, compared to SVM and other methods, this not so sensitive. Just give one, just try 1 or 2 times. Usually okay, right? It can be efficient for batch mode learning or the sequential learning. One part incremental learning was not mentioned here. Actually, it's all very interesting. This comes from our ERM theory. For ERM different from other methods. Any major algorithms of ERM come from theory. So that means any algorithm with a proof in theory. Okay, any major theory in ERM resulted in a learning method. So this is different from other methods. Other methods usually come from idea, but kind of proof. Okay, sometimes you can prove something in the neural network, but no algorithm to support. Say number of hidden node can go to infinity. How to implement it? That's a problem, right? Of course, ERM work for different hidden nodes. it also include kernel. If HX is none, random generated. If HX are none, you can also use the same as kernel as SVM method, just using kernel, right? So HX can be ignored. Okay, so then here is, of course, learning is very fast. Usually you say SVM can be some method on this square, say for one case, 3 hours, 7 hours, right, to complete one case. Then ERM just even less than 1 second. So in this case, in this sense, it can be, can we do something on real-time learning? Okay, and especially also the online sequential learning can also be used in real-time cases. Then the next two, this morning I added. I just mentioned. So ERM, or if we talk about the traditional SVM, okay, even talk about the least square, traditional SVM search the best result in the hyperplane within the cube. If we compare the same method, ERM search the best result in the entire cube. So in this sense, ERM always provide a better general performance because definitely won't worse than the result generated from a hyperplane in that cube, right? And also,
the parameter space is different.
The same.
No, SVM usually has a bunch of.
No, the same. You look here. This actually.
Dimensionality is different.
The same.
You have more.
No, the same.
Higher dimension.
You see here. You look at this. This is the optimization target of SVM, right? So TI, phi. Okay. You see here the same. And so in the.
But in general, the N used in SVM is much bigger than the N used in the.
No,
in your
N here the same. N here is the number of training data. So you say the training data is same. Then we use the same kernel, same feature mapping. Phi in SVM. So H in ERM, they use the same one. Say for example, and then the condition for ERM is here. The condition for SVM is, add one more, right? So usually better because we in ERM case we request feature mapping satisfy universal approximation even on long should be because if you can't satisfy universal approximation, that means some black hole there, right? Some case it can't be.
I haven't follow much about this universal approximation because people typically consider to be theoretical interest. Now, in your case, for the universal approximation condition to be held, do you? I remember a long time ago when people wrote proof that the universal approximation condition, they have to assume that you have to do certain amount of learning. I kind of
maybe we can. You can discuss. You have time.
Okay. Okay. So then similar to this square SVM, the same case. Okay, the same case. So then go back to your earlier question. So why ERM say random generate good? Okay, intuitively speaking, why is it good? So in the beginning, in the 5 years ago, I have no idea. Then I always try to think of some idea why it's good. So I always talk this story to my students and also other researchers. Okay, in the beginning, even myself, I do not believe. So what is the natural phenomena very similar to this case? Say China, right? In China, Hangzhou have West Lake, right? Wuxi have a West Lake, so-called Taihu Lake, right? So lake, we want to fill up the lake, okay, a river. You see the bottom. Bottom is a curve. Bottom is a function. So two type of people to fill up the lake. One is engineer, another is farmer. So how does engineer fill the lake? Engineer have to pump out all the water, measure the curve of the bottom to see what's the size, what's the curve, sampling, get the training data first. And then, okay, so they're training that. Then do a lot of research. How many students I can use to fill up the lake? 1,000 students, 10,000 students, or 100 students? Fill the lake. You move the student to fill the lake. Of course, fill the lake means go to the horizontal, right? It's horizontal, okay? So each student used by the engineer looks like a hidden node. So then the engineer had to measure, had to calculate. where to put this student. This student so big. Put here, maybe overfitting, too large. Put there, so they have spent a lot of time find a location, right? If 1,000 is still not enough, can we add another one? Where to put? So this is the BP learning method. Now, farmer comes. Farmer has no knowledge, right? It does not know how to do calculation. Very simple. Good. We have a larger mountain, the Himalaya mountain, using a boom to explore the whole mountains. Then generate the random size of stones, rocks, big size, small size, even sand. So then how the farmer fill in that lake? Use a truck. Random, right? Pick random number of stones, random number of size of stones, push to the lake. Random put here, here, here. What is that? That is random generated. So when the farmer use a truck to take the stone, does he need to know what's the size, what's the training, some of the training data from the lake? No need, just the random generate a stone. Then put random here, here, here. So which one faster? Of course, farmer's method is much more efficient. And does the farmer care about how many stones need to be used? No need. As long as the least square error means the error smaller, okay, right? So then what is the beta used by the farmer? For the engineer, he has to calculate the size, the height of the stone. But farmer can go there using something, just smash the stone. If this is too large, right? We suppose the beta indicates the height of a stone. Right? If the beta equal to 0, the height of the stone equal to 0 means nothing. Even you put a stone there, that means hidden node put there, you can smash the stone to make the height of the stone 0. So definitely farmer method is more efficient. Right? So then even for farmer method, does it care about do you have 1,000 hidden stone or 1,001 hidden node? No, it doesn't matter. Even if you have more, it doesn't matter. I can smash the height of the stone, make the beta become 0, right? Even if you have 10 minutes, it doesn't matter, all becomes 0. So this is why ERM works. Yeah.
But there's an interesting analogy here. Actually, I appreciate what you said earlier on that when you randomize your lower layer parameters, you don't need to have all the data. And then in that case, you minimize sort of the early decision in terms of the discrimination.
Yeah.
And there is actually similar kind of technique now neural net people develop. I don't know whether it's not in maybe different community. It's mostly in NIPS community. They actually talk about this RBM, restricted bottom machine. They have similar kind of philosophy of not using the target in initializing parameter, but they actually use the data for reconstruction of the data to make sure that whatever hidden you might have, you get minimum error in restructuring the data, but if they discard entirely the output.
Yeah.
And once they do that, they actually tend to do better in the conditional backpropagation.
Yeah.
Starting with the random initial.
Yeah, this is possibly right. So this is why.
Similar kind of.
Yeah. I think so. They may have some kind of common so-called sense behind. So that means when we do hidden layer, some parameter may not be related to your target.
No, but the whole power of that approach is that allows you to build the representative layer by layer all the way up there. Wow. So that comes back to some of the ELM coming to see whether you actually use this not only for one hidden layer, but keep building up the layers using similar kind of philosophy, maybe randomizing things.
Yeah, great idea. So here we talk about the hidden layer. We say the hidden layer HX. So sometimes we say HX is unknown or HS is something else. It's not just one hidden node. It may be a lot of network there. Maybe a lot of hidden layer there. So
you show that when you build more.
Yeah.
Layer by layer for this.
Yeah, that's right. We didn't show layer by layer, but in our theory, we say HX may not just a single single hidden node. It can be just any kind of computational hidden node. It can be a lot of network, a lot of layer. But in theory, you already prove it.
You should try to see whether you build from the lower up, you get better result. If you do that, then we can.
Yeah, they may be more powerful. But in this case, we haven't tried it yet. But that is one of the good directions. In theory, we have something related. That means HX may not just a so-called RBF hidden node or some kind of kernel. It may be a other computational node. It can be a system even. So this is why I do not intentionally use neuron here. I wish to use a node, a computational node. This can be a system. It can be a single output function, whatever.
Okay, great.
Yeah.
Last question.
Sorry for
online scheme. So I'll ask this. I have a couple, but I'm asking the one, the small one. So in online learning scheme, so would you have to incrementally sort of adjust the number of hidden nodes?
Okay, so actually we have the two type of learning methods for online. So one is called online sequential learning. So here is the many focused case where the data coming one by one or chunk by chunk. Or in this case, the network architecture is fixed. So then whenever the data coming, of course, some parameters of the network have to be tuning, especially for beta output weight. So another so-called technique we call incremental learning. Of course, this definition may be different from others' incremental learning. So that means the data is fixed, or the data also coming, but the network architecture can also be updated. So both the parameter and network architecture can be updated. That is another one. That is also very, very efficient. We prove in all the cases it is better than SVR, support vector machine for regression. That is actually already published in the so-called actually in the TNN. That is also comes from why. Okay, that is. Let me show here. that is published here. So this is why this theory actually generated that algorithm. Okay, actually this theory also comes from that algorithm. We consider intuitively that algorithm works. Then how to prove it? That is very, very difficult to prove. We have to appreciate the fair review, professional review from this journal, and also the editor, past editor-in-chief of this journal, because the review took 3 years to complete the review, 7 reviewers. Of course, in the first version of the paper, the proof is totally wrong. But then the reviewer very kind and say, the result is right. So then I work with my student, try to correct the proof, but all proof is based on another published paper. Actually, the proof in that paper also wrong. So then we didn't note the proof in that paper wrong. So we take a long time and find the proof in that paper wrong. So then we try to correct. But I correct my student also from the math department. So then he said we may able to use the proof in that paper. So we try to correct the proof in that paper. So then we try to do it. But just 1 week before we submitted this paper, we also found that no, all correction is also not correct. So then we totally ignored. Then we use the topological method to correct it. So finally it works. So this is very interesting. So finally the algorithm generated from that theory actually is very, very efficient. I just took out these slides this morning because I found that too many pages here. Yeah.
Great. Okay. Let's thank.
Thank you so much.